Earth's gravitation. Gravitation near Earth's surface. One, Earth is not a uniform. Second, Earth is not a sphere, it's an ellipse. Earth is rotating. So, the gravitation acceleration we measured is changing around the Earth. First, it changes from region to region. Second, it different from at equator and the poles. Third, with different attitude in the same place above the Earth is different G. Let's look at the stuff sit on the Earth and rotate together with the Earth. How many forces acting on it? Two. One is the gravitational force towards the center of Earth. Another is normal force perpendicular to upstate. And it actually the normal force is its weight. Now we see MAG, we call the gravitational force caused by the gravitational force. This is gravitation acceleration. And we see because it rotates, so the gravitational force downward minus the normal force equal its centripetal force, m omega squared up. And this m actually is the weight we measure, mg. So that's why we have mg equal to mag minus m omega r. That means the measured weight equal to gravitational force minus centripetal force. If you take the m off, you have g equal to ag minus omega squared r. This is the centripetal acceleration. So we have the free fall acceleration equal gravitational acceleration minus centripetal acceleration. Sample. An astronaut whose weight h is 1.7 meter floats free down in an orbiting space shuttle at a distance r 6.77 times 10 to the 6 meter from the center of Earth. What is the difference between the gravitational acceleration at her feet and that at her head? Now we know the acceleration outside is ag equal to gm, the Earth, and over r squared. You put the small m, put the small n, this ma equal to gravitational force. Now, how would you find the difference between the acceleration between her feet and head? And we can do, after we have learned to calculate, we can also really get a dA. dA. This me is the mass of Earth. dA is the difference. We do the differentiation with respect to r. So we do the dA equal to mg constant e, r squared, 1 over r squared derivative equal to minus 3r cubic, and the dr. And we see what is the acceleration difference? This is a g minus 2. This is mass of Earth. dr. This is r. R is this one, and the dr is 1.7. We put this number inside, we get it. The acceleration difference is minus 4 times 10 to the minus 6 meter per second. Very, very small. Gravitation inside Earth. We know the gravitation force equal to g m1 m2 r squared. We have two factors. If we were moving inward, perhaps down a deep mine shaft, the gravitational force would change for two reasons. One is r getting smaller and smaller, so f getting larger. Second is m2 getting smaller and smaller, so the f getting smaller. Why m2 is smaller? Because according to the Newton's shear theory, all this mass outside the point it acting no net gravitational force. For a uniform Earth, the second influence would prevail, and the force on particle would steadily decrease to zero as a particle approaches the center of Earth. However, for the real non-uniform Earth, the outer crust is so much less dense than the core that the second influence above is greatly weakened, and the first influence prevails. That is, the gravitational force on the particle would increase slightly as we lower the particle down a deep mine shaft. Eventually, of course, the force would reach a maximum and then decrease to zero at the center of Earth.